Already, all of you know that I have discussed many times. In ideally, the inverter should carry the sinusoidal waveform from the output side. But practically, what happened? Practically, the output voltage obtained from inverter is not sine wave. Basically, it consists of fundamental component as well as the harmonic component. Due to the presence of harmonics, the output voltage waveform of inverter leads to poor performance and reduce the system efficiency. Several techniques are used for reduction of harmonics, so the output voltage obtained, which can be the less uh, harmonic content, and thereby the several techniques are used or are incorporated for harmonics reduction. Always we should the lower the harmonics content in the output voltage waveform, better quality of the inverter. So thereby the several performance parameters which evaluated the quality of inverter, and that is number one, the harmonics factor of nth harmonic. What is harmonic factor of nth harmonic? It is defined as the ratio of RMS value of nth harmonics voltage component to the RMS value of the fundamental voltage component, which is identified by rho n equal to V on to the V01. That means from here it is very clear that, so here V1 is the RMS value of nth harmonic component of output voltage, and V01 is the RMS value of fundamental component of output voltage. Suppose if suppose the RMS value when contain the fifth harmonic component of the output voltage, then what happened? See, for example, if the harmonic factor of fifth harmonic is rho 5 equal to V1 to the V05, here V05 is the RMS value of fifth harmonic component of output voltage. So the harmonic factor, so thereby you can say the harmonic factor is a measure of the contribution of any individual harmonic at output inverter voltage. Next is that the total harmonic distortion. It is also known as the THD. The total harmonic distortion is defined as the ratio of RMS value of all the harmonic component to the RMS value of the fundamental component. That means here you can say, if we write the THD equal to, you can write THD equal to this is the RMS value of all harmonic component VOH, and this is your V01 is the RMS value of fundamental component. Now the fact is that how you get the RMS value of all harmonic component? Yeah, VOH equal to under root over V1 square minus V01 square. Yeah, V01 is the fundamental value of component, and VOR is the RMS value of inverter output voltage, including the fundamental plus all harmonics. Fundamental plus all harmonics. So thereby you can write the THD equal to, just replacing only VOH, so under root over V1 square minus V01 square to the V01, which is equal to VOR divided by V01 minus 1. So here, what is this? THD is the measure of the waveform distortion. Low the value of THD, low the value of THD, and see, lower the amount of distortion in voltage or current waveform, and therefore it is closer to waveform to sine wave. Actually, see, we should mind it. Whatever we shall go and we shall do for performance parameter, because we should go near to sinusoidal waveform, of output voltage of the inverter. Should go. Next is the distortion factor. It is defined as the ratio of fundamental RMS output voltage to the total RMS output voltage. Therefore, here you can write the distortion factor is equal to mu equal to B0 P over. Yeah, here you can replace by if you replace by using mu. So you can write one divided by mu square minus one to the power half. And mu we can relate it mu equal to 1 divided by 1 plus THD square to the power half. Actually, this is the relation between the distortion factor and the total harmonic distortion. Always, if we do like if we analyze this the relation between the distortion factor and the total harmonic distortion, you see a higher value of distortion factor, how much value of distortion factor maximum to reach? It can be it vary from 0 to 1, so it can be reached to the closer to unity, and lower value. So the lower is the magnitude of harmonic component of the output waveform. So distortion factor, if will reach near to unity, that means that total harmonic distortion is less from in your system. And another is the lowest order harmonics, which is LOH. The lowest order harmonic component with a magnitude greater or equal than 3% of the magnitude of the fundamental component of the output voltage is known as the lowest order harmonic. This is the another thing, and some books are not given this lowest order harmonics parameter. So you should mind it. And another thing, the higher the frequency of your lowest order harmonic, lower will be the distortion. So all are associated, all parameters, whatever you have seen, the nth harmonics component, the total harmonics distortion, the distortion factor, and the lowest order harmonics, all are associated with them. All are associated with them. This is the parameter. And whatever you have done from your single phase half bridge inverter, full bridge inverter, and in your performance parameter of the inverter. So based on this, you have some numeric. So if possible, I shall go ahead for numeric class, but till you can go ahead for numeric. There are many numerics are there based on the single phase full bridge inverter, your half bridge inverter, yeah, and the other parameter. How the your what is the derivation actually from the inverter? Actually, see, it can be happen. Suppose if we consider a full bridge inverter, which is using a transistor diode, and if feeding the load, supposed to say when the load will identify, and your obviously input DC will identify, then you can identify from this thing what is the RMS value, what is the output voltage, what is the fundamental component of the output voltage, what can be the output power, what is the fundamental frequency output power, what is the average and peak current of each transistor, the peak reverse blocking voltage of each transistor, and harmonic factor, your total harmonic distortion. So it can be analyzed. It can be analyzed, and we can do this. Is it visible for you? See, is it visible for you? Whatever I'm saying.
No, sir.
Now?
Yes, sir.
Okay, okay.
Yes, sir.
Now see, I shall go to the another thing, which is voltage control in single phase inverter. Basically, basically, AC loads actually may require the constant or adjustable voltage at their input terminals. When such loads are fed by the inverter, it is essential that the output voltage of the inverters is so controlled as to fulfill the requirement of AC loads, such as you can say how they actually do this, how they control the voltage as the required sometime we have required for application purpose the constant voltage and adjustable voltage. So thereby some things are there. What are they? An AC load may require a constant input voltage to a different level. For such a load, any variation in the DC input voltage must be suitably compensated in order to maintain the constant voltage at AC load terminal and at a desirable level. And another thing is that in case inverter supplies power to a in case any inverter, not only that the inverter, in case any inverter supplies power to a magnetic circuit, such as your induction motor and your other rotating machines, the voltage to frequency ratio at the inverter output terminals must be kept constant. To avoid the saturation in the magnetic circuit of the device fed by the inverter and the variation fed by the inverter. There are various methods are there for control the output voltage of the inverter. The external control of AC output voltage and external control of DC input voltage and internal control of inverter. Basically, here the external voltage control of the output and external control of DC input voltage methods, the use of peripheral component, required to use of peripheral component. The external control voltage. How the external control voltage is there? How? There are two possible methods of external voltage control of AC voltage obtained from inverter output terminal. Basically, the methods can be employed your AC voltage control and series inverter control. The AC voltage control, there are lots of systems are there to control there are systems are there to control the AC voltage and as well as the series inverter control. How? See, the AC voltage control, in this method, an AC voltage controller is inserted between the output terminal of the inverter and the load terminal as here identified in the circuit T. See, if we apply the constant DC voltage to the inverter and corresponding here AC voltage regulator is incorporated and thereby you get the controlled AC voltage as required for your variable load in your load side. So to get the controllable output from the inverter. So thereby you can control the inverter voltage because as you are given the fixed DC inputs, obviously you will get the fixed output, thereby AC voltage controller is employed here to get the variable AC output. Here the see how we can do this. See, the voltage input to the AC load is regulated here through the firing angle control of AC voltage controller. Only by changing the firing angle, we can get the output, and the method gives rise to higher harmonic component in the output voltage. Particularly when the output voltage from the AC voltage control is at low level, this method is rarely employed except for low power application. So it can be because due to the generation of harmonics in the output side. Only this type of application is employed for low power application. So low power application because when you change the firing angle of the AC voltage controller, so thereby the harmonics can be generated, and due to the generation of this, generation of harmonics, so we will get the low power. So thereby it can be employed for low power application. Next is that the series inverter control method. Actually, in this method, the voltage control involve use of two or more inverter in series. From the figure, it has been shown that from the figure, it is shown that there are two inverters are there. The output voltage of two inverter can be summed up with the help of transformers to obtain an adjustable voltage, and the inverter output is fed to transformers whose secondary are connected in series. Uh, which secondary are connected in series. See, here this is the constant voltage. This is inverter 1, inverter 2. This is primary. The primary side is split into coil. See, this is the primary side of inverter 1. This is the primary side of inverter 2, and thereby the secondary is there. But secondary coil is shorted. There is no classification there. Corresponding, you are getting the output voltage. And if you see the phasor diagram, you can see the this is voltage for V0 and this is V02, and corresponding you are getting the output voltage. That means this is a parallelogram type. If we consider this is P, this is Q, and thereby you can get the resultant value. The resultant is P square plus Q square plus 2PQ cos theta, if the angle is theta under root 1. So this is the same configuration. If you draw the phasor diagram, so corresponding you can get the corresponding you can get the phasor diagram, and here everything is given illustrate. So there is no problem. I hope you think. And now see here it is essential that the frequency of the output voltage V01, V02 from the two inverters are same. When the theta is zero, that means output voltage will be sum of two inverter voltages V01 and V02 respectively. And for theta equal to 90 degree,